Welcome, dear listener, to The Lazy Scientist. It's wonderful to have your company this evening. Before we settle in, I'd love to know, where are you joining me from tonight? Maybe you're tucked into a quiet bedroom, drifting on a late-night train, or lounging peacefully on a soft sofa with a steaming cup of tea. Wherever you find yourself, my hope is simple, that you feel safe, cozy, and gently ready to wander with me into thought. If you find comfort in these soft explorations and want to hear more of them, consider leaving a like and subscribing. It helps this sleepy little corner of the internet float along. And to those who are already subscribed, thank you from the bottom of my heart. Your support keeps this channel alive more than you can imagine. Now, I'll try my very best not to make tonight's topic so captivating that it keeps you awake longer than you'd like. But if curiosity does keep you turning, you might drift away with a deeper understanding of why the tiniest particles sometimes pretend to be waves, and why reality itself seems to pause until we pay attention. If sleeplessness comes as the cost of wonder, perhaps it isn't too steep a price. So, let's begin, shall we? What exactly is quantum physics? And why does it so often sound like the universe is improvising its rules as it goes along? The world you know, the one you can touch and see, appears solid and reliable. A cup slips, and gravity ensures it falls. Toss a coin, and it obediently lands on one side or the other. Close your eyes, and the moon doesn't wink out of existence just because you've stopped looking. Reality seems steady and predictable. But at the dawn of the 20th century, scientists dared to look closer. Much, much closer. And the more deeply they peered into matter's inner workings, the more peculiar everything became. Light, that familiar companion, revealed itself to be a trickster, sometimes acting like a smooth, endless wave, other times as discrete, bouncing particles. Particles themselves, once thought of as solid building blocks, turned slippery and uncertain. They could exist in multiple states or locations until someone checked in on them. And strangest of all, observing something didn't just uncover what was already there. It seemed to change it. This wasn't the result of bad instruments or sloppy notes. It was repeatable, undeniable, and completely at odds with the tidy rules of classical physics that had reigned for centuries. Quantum physics wasn't just another branch of science to be catalogued. It was a whole new lens on reality, a shimmering, elusive way of seeing the world where probability often replaces certainty, and where causes don't always line up neatly before their effects. In this gentle video, we'll wander slowly through that world. No need to wrestle with every equation or memorize every name. We'll take our time, softly, one puzzle at a time. From the earliest hints that cracked open the polished shell of classical science, to the modern mysteries that still keep brilliant physicists lying awake. So, nestle in, perhaps close your eyes if you wish, and let's set out on an exploration of a universe where empty space isn't really empty at all, and where everything you thought was certain turns out to be only probably true. At the turn of the 20th century, physics felt nearly complete. The great laws of motion were neatly laid out, thermodynamics appeared well ordered, and light seemed secure within the grand framework of electromagnetic theory. Many declared it a golden age of intellectual certainty. Some scientists even boasted that the big questions had already been answered, with only a few dusty corners left to tidy up. One of those supposedly minor puzzles had to do with something so common you might see it in your fireplace or kitchen stove. What happens when an object is heated? Warm a piece of metal or coal, and it glows. First a faint red, then a brighter orange, eventually a dazzling white as the temperature climbs. This glowing, known as blackbody radiation, arises because heated objects emit electromagnetic energy. Observing it was easy, explaining it was another matter. Classical equations predicted something bizarre. According to the math of the time, a black body should radiate increasing amounts of energy at shorter wavelengths as it heated, particularly in the ultraviolet spectrum. That would mean infinite energy pouring out of an object at high frequencies. Clearly impossible. Physicists grimly nicknamed it the ultraviolet catastrophe. No amount of tinkering could rescue the classical formulas from nonsense. Something was deeply missing. Into this mess stepped Max Planck, a German theoretical physicist, in 1899. Planck was cautious by nature, not the type of radical rebel one might expect to ignite a scientific revolution. He believed in the classical worldview, but he was also pragmatic, willing to adjust when reality demanded it. Faced with the stubborn radiation problem, Planck tried something unusual. He proposed that energy couldn't be emitted in any arbitrary amount. Instead, it arrived in tiny, indivisible packets, like coins that couldn't be split smaller. These he named quanta. This was a daring departure from the old idea of energy as a continuous stream. Planck introduced a constant, later called Planck's constant, to define the size of these packets. Though unimaginably tiny, this constant brought elegance to the equations. And once he inserted his new idea, the catastrophe disappeared. The predictions finally matched experimental results. Planck had resolved the impossible infinities. Yet, in his heart, he didn't fully believe his own solution. He described quantization as a clever mathematical trick, an accounting convenience, not a literal description of reality. Surely, he thought, a better explanation would one day replace it. What he couldn't foresee was that this temporary patch would become the cornerstone of an entirely new worldview. His little constant lit the match that would burn slowly into the foundations of physics. By the early 1900s, light seemed comfortably understood as a wave, thanks to Maxwell's equations. With Planck's quiet adjustment, most physicists assumed the story was more or less complete. But then came another riddle, this time involving light striking metal. Experiments showed that when light shines on a metallic surface, electrons can be knocked free. It seemed straightforward. Light delivers energy, and that energy ejects electrons. According to wave theory, making the light brighter should give more energy to the electrons. But the experiments refused to cooperate. Brightness alone didn't guarantee electrons would escape. What mattered was the frequency of the light. Below a sharp threshold, even the brightest beam did nothing. Above it, even a faint beam knocked electrons loose with ease. Enter Albert Einstein. In 1905, his miracle year, Einstein offered a bold explanation. He proposed that light was not only a wave, but under certain circumstances behaved like a particle too. Tiny packets of energy, later known as photons. Each photon's energy depended on its frequency. If the photon carried enough energy, it could liberate an electron. If not, no number of photons could succeed. This leap built on Planck's quanta, but went further. Einstein wasn't treating quanta as a bookkeeping trick. He insisted they were real. Light itself was made of these packets. It was shocking. Light clearly behaved as a wave in many contexts. How could it also be a particle? Einstein didn't discard the wave picture. He insisted light was both, depending on how it was observed. This strange duality defied classical categories, but Einstein's explanation fit the experiments perfectly. Low-frequency light, no matter how bright, simply lacked the punch to eject electrons. High-frequency photons, even in small numbers, did the job. In 1921, Einstein received the Nobel Prize, not for relativity, as often assumed, but for this explanation of the photoelectric effect. And yet, even Einstein grew uneasy with quantum theory's stranger implications. He famously protested, "God does not play dice." Still, the dice were rolling. Now imagine a simple setup: a flashlight, a piece of cardboard with two slits and a screen. Shine the light, and you'd expect it to act like a wave, and it does. Two slits produce an interference pattern of bright and dark bands. No surprise there. But lower the intensity until only one photon at a time passes through. Surely, these single particles should behave like tiny bullets. Two neat clusters behind the slits. Yet, over time, they build the same interference pattern as before. It's as though each photon interferes with itself, traversing both slits simultaneously. Physicists tried to peek, adding detectors to track the photons' paths. The moment they looked, the interference vanished. Photons behaved like ordinary particles again. Stop observing, and the wave pattern returned. It wasn't disturbance from the detectors. It was the act of observation itself. Reality seemed to decide only when watched. This experiment has been repeated with photons, electrons, even molecules of hundreds of atoms. The result is always the same. Left unobserved, particles behave like waves, existing in shimmering possibilities. Observed, they collapse into definite states. The double-slit remains one of the most haunting experiments in physics. It hints that reality, at its deepest levels, is tied to observation, that information itself carries weight in shaping existence. What began with the faint glow of heated metal and the stubborn math of black-body radiation unraveled into a world stranger than imagination. A universe where energy comes in packets, where light is both wave and particle, and where the simple act of watching can change the story entirely. Quantum physics didn't merely add new equations, it reshaped how we think about reality. It whispered that certainty is rare, that probability rules, and that the universe may only reveal itself when asked. So, as you drift off tonight with the lazy scientist, remember, the world around you is not as simple as it seems. Beneath the calm surfaces of cups and coins and moons, there's a hidden dance, one both chaotic and precise, both uncertain and strangely ordered. Close your eyes, let your breath slow, and surrender to the thought that reality itself might be waiting for you to dream it into being. These aren't just abstract or poetic ideas. They are scientific questions, rooted in experiments, measured carefully, and confirmed again and again. The famous double-slit experiment doesn't give us simple answers, but it does give us one extraordinary insight. The universe is not a rigid machine grinding away like clockwork. At its very core, reality is a luminous tapestry woven from countless possibilities, and it behaves in curious ways when we dare to look at it. With nothing more than two slits, a beam of light, and a waiting screen, we've learned something astounding. The universe seems to wink playfully when no one's watching, and it freezes into certainty when we are. In the world of quantum physics, if one mathematical expression carries the weight of a secret incantation whispered throughout the entire theory, it is Schrödinger's equation. But don't worry, this is not going to become a midnight lecture in calculus. Nobody climbs out of bed hoping to dream of partial differential equations. And yet, this particular equation deserves attention. It isn't just chalk scrawled across a blackboard. It's the quiet, steady heartbeat of the quantum universe. Back in the 1920s, physicists were grappling with particles that refused to act like particles. Electrons created wave-like interference. Photons slipped between realities like ghosts of probability. Newton's clockwork laws, the ones that guided planets and apples, were breaking down at smaller scales. A new kind of language was required. Enter Erwin Schrödinger. In 1926, he introduced an equation that could describe not only how particles moved, but how their associated wave functions flowed and evolved over time. It was elegant, compact, and astonishingly powerful. On paper, it may have looked like a forest of Greek letters and mathematical operators. But at its heart, it told a remarkably simple story. It explained how a quantum system changes. The essential idea here is the wave function, usually written with the Greek letter psi, xy. If that feels abstract, think of it as a quiet mathematical whisper, carrying everything we can know about a quantum object, where it might be, how likely it is to show up there, how it may be moving, and what its tendencies are. The wave function doesn't hand us definitive answers. It offers probabilities. In classical physics, if you imagine a particle as a tiny dot, you can draw an arrow showing exactly where it is and how fast it's going. But in Schrödinger's framework, the particle becomes a hazy ripple of possibility, a cloud that says it's most likely over here, but perhaps also there, and maybe even a little up there too. Here's where the beauty begins. Schrödinger's equation tells us how that probability cloud evolves with time. Instead of tracking a single point, it follows the shimmering fog of possibilities as it ebbs and flows. And when we measure the particle, when we finally demand, "Where are you?" the cloud collapses in an instant, leaving behind a single definite answer. Only then does the particle reveal itself. This perspective is profoundly different from the mechanical universe Newton described. Instead of neat orbits and predictable trajectories, we now find waves of uncertainty, delicate ripples of chance, persisting until observation pins them down. To make it more visual, imagine being blindfolded in a room. Somewhere nearby is a silent cat. You can't see or hear it, but you toss small balls across the floor and listen for the faint sound of impact. Over time, you build up a mental map. Some places are more likely, others less so. That evolving mental picture is like the wave function. It isn't a perfect image of reality as it is, but rather of reality as it might be. Now imagine you could write an equation that tells you how that mental map shifts over time. Maybe the cat prefers warm corners or likes hiding under furniture. That equation would guide your expectations. That's what Schrödinger achieved, except his focus wasn't cats, but electrons. The mathematics flows smoothly, describing waves of probability that ripple like water in a pond. It respects deep symmetries of nature, such as the conservation of energy and the steady march of time. Yet it offers no guarantees. It maps what could happen, not what will happen. And the astonishing part, it works. With uncanny precision, Schrödinger's equation has described everything, from the arrangement of atoms to the binding of molecules, from the functioning of semiconductors to the strange behavior of superconductors. It even predicts mind-bending effects like quantum tunneling, where particles sneak through barriers they should never be able to cross. One of its triumphs came with the hydrogen atom, the simplest of all atoms. Before quantum mechanics, no one could explain why electrons seem to settle into stable orbits instead of collapsing into the nucleus. Schrödinger's math revealed that electrons don't whirl around like tiny planets. Instead, they form standing waves, patterns of probability that settle into beautiful, stable shapes around the nucleus. These shapes, called orbitals, are the cloudy patterns you may have seen in textbooks. They aren't artistic guesses. They are literal maps of where electrons are most likely to be found. Unlike patchwork theories that constantly need fixing, Schrödinger's framework has aged with grace. It continues to deliver, century after century. Yet, it remains elusive. You can't hold a wave function in your hand. You can't peek at one directly. And yet, its predictions are undeniably real, from the particles in your cup of tea to the chips inside your phone. Still, a deeper question lingers. What is the wave function? Is it merely a reflection of our limited knowledge, or is it a real, physical entity smeared across space until measurement collapses it? Physicists still debate this fiercely. Schrödinger himself was conflicted. While proud of his elegant equation, he disliked the unsettling conclusion that reality didn't exist in definite form until someone looked. His now-famous thought experiment of a cat alive and dead in a sealed box was not meant as proof, but as protest, an attempt to highlight the absurdity of the implications. Nonetheless, what he gave us remains one of the most beautiful achievements of human thought. His equation does not bark commands. It flows, it whispers, and it guides us gently through a universe that is softer and more mysterious than we once believed. At these microscopic scales, motion is no longer always motion, position is not always position, and certainty becomes a rare luxury. Yet, with Schrödinger's guidance, we can still navigate the haze with elegance. Now, in the familiar everyday world of apples, bicycles, and bowling balls, knowing both where something is and how fast it moves is trivial. A radar gun clocks a car's speed as GPS tells you its exact spot. No puzzle, no contradiction. But the quantum world doesn't obey such rules. In the late 1920s, Werner Heisenberg unveiled a principle so counterintuitive, so fundamental, that it continues to puzzle and inspire. The uncertainty principle. It declares that at the smallest scales of existence, there are limits to what can be known. The more precisely we pin down a particle's position, the less precisely we can know its momentum, and vice versa. Momentum, simply put, is mass multiplied by velocity, the measure of motion. In daily life, this principle sounds absurd. If you see a train pulling into a station, you know exactly where it is and how fast it's moving. But electrons do not grant us such clarity. And crucially, this is not due to clumsy instruments or imperfect technology. The uncertainty lies in reality itself, built into the mathematics of quantum mechanics. Shine light on an electron, and the photons will disturb it. Even if you imagine some ghostly way of observing without interference, the uncertainty persists. It is not a bug. It is a feature of the cosmos. The principle stems from the wave-like nature of matter. Try to locate a wave in the ocean. You can point to a crest, but the wave is spread out. Similarly, an electron's wave function is a fuzzy cloud. A wide, smooth wave allows momentum to be known with fair accuracy, but hides position. Narrow the wave to locate position precisely, and momentum scatters chaotically. It's a cosmic trade-off written in stone. Mathematically, the product of position uncertainty and momentum uncertainty can never be smaller than Planck's constant divided by 4 pi. It's a tiny number, invisible in baseballs and cars, but dominant in atoms and subatomic realms. This strange rule explains why atoms don't collapse. If an electron fell into the nucleus, its position would be perfectly known, forcing infinite uncertainty in momentum and requiring infinite energy. The universe forbids it. Instead, electrons hover in stable patterns, protected by uncertainty itself. Think of it as trying to clutch mist in your hands. The tighter you grip, the less remains. Loosen your hold, and more lingers. That is the balance quantum mechanics enforces. Far from chaos, uncertainty is structured ambiguity. It grants the universe texture. It allows tunneling, stability, and even chemistry. Without it, existence would be too rigid for life to bloom. Heisenberg's revelation was not a failure, but a reminder. Not all truths can be sharp-edged. Some truths are necessarily soft, clouded, and unresolved. And perhaps that is what makes them beautiful. Now let's step further into strangeness. In daily life, things are binary. A coin lands heads or tails. A switch is on or off. A drink is hot or cold. But in the quantum realm, this neat division collapses. Particles can exist in superposition, where multiple states coexist at once. Imagine flipping a coin. In classical reality, it's one side or the other throughout its flight. You just don't know which until it lands. But in quantum reality, the coin is not hiding its result. It genuinely exists in a blend of heads and tails until observation forces a decision. Superposition was introduced to explain the behavior of particles like electrons and photons. Rather than following a single path, they exist as wave functions containing every possible state simultaneously. Each option, spin up or spin down, photon left or right, is woven into the math. Only measurement collapses the fog into one outcome. Picture a misty valley. The particle is not walking a trail, but smeared across all of them. Your measurement is like a flash of lightning that instantly illuminates one hilltop, freezing one outcome into reality. This led Schrödinger to devise his most famous thought experiment, the cat in the box. Inside, a radioactive atom, a detector, and a vial of poison create a peculiar situation. If the atom decays, the cat dies. If not, it lives. Until the box is opened, quantum mechanics says the atom exists in both decayed and undecayed states. And so the cat is both alive and dead. Schrödinger intended this to highlight absurdity, not literal truth. Yet it perfectly captured the eerie implications of superposition. And far from being a flaw, superposition has become a feature central to modern science. Quantum technologies depend on it. Take quantum computing. While classical bits are either 0 or 1, quantum bits, qubits, can exist in a superposition of both at once. This allows them to carry far more information. Entangled together, qubits can represent staggering numbers of possibilities simultaneously. This isn't magic. It is mathematics, rules of nature applied to computation. Superposition, once an oddity, is now the foundation of a revolution in technology. Problems that once felt impossible, like simulating intricate molecules or optimizing giant networks, suddenly become approachable, and the key to that shift is the capacity of qubits to exist in superposition. You also find superposition at the heart of quantum cryptography, where it helps guarantee that information cannot be intercepted without leaving fingerprints. In quantum sensing, the same principle allows scientists to notice vanishingly small changes in magnetic fields or tiny ripples in gravity. These are not flights of science fiction. Real devices are being designed and tested right now. There is a catch. Superposition is fragile. Quantum states bruise easily. A touch of the surrounding world can unravel them. Stray photons, trembling vibrations, or even a brush with wandering air molecules can make a delicate wave function collapse. This loss of quantum behavior is called decoherence, and it is one of the biggest hurdles in building reliable quantum machines. Picture trying to balance a feather on the point of a pencil while someone in the next room keeps sneezing. The instant your system bumps into the environment, the superposition evaporates. That brittleness is part of what makes quantum systems so captivating. They offer remarkable power, but only when treated with care and isolation. They grant access to probabilities rather than promises, and invite us to rethink what it means to say that something exists. Which raises a deeper question. If a particle can occupy multiple states, is that a fact about the world or a reflection of our knowledge about it? Some interpretations say the wave function is like a ledger of information, our best description until we measure. Others claim it is a physical entity, and the particle truly is spread among many possibilities until a measurement forces a choice. Either way, quantum superposition asks us to loosen our grip on classical logic. It says that opposites can live together. A system may be this and that, here and there, yes and no, all at the same time. Reality looks less like a single thread and more like a woven tapestry of overlapping possibilities that remain unresolved until observation tugs out one strand. It can feel strange or uncomfortable, yet there is beauty in it. In this rule of superposition, the universe becomes flexible rather than stiff, poetic rather than mechanical. Contradiction and uncertainty are not defects, they are features. And with that perspective, we find new paths for computing, new channels for communication, new instruments for exploration, and new ways to imagine what is possible when reality resists making up its mind. Now imagine two gloves, one left hand and one right hand. You place each glove into a separate box and ship them to opposite sides of the world. You are not sure which box holds which glove. The moment you open one and see the left glove, you immediately know the other must be right. There is nothing mysterious there. The gloves had fixed identities all along. Quantum entanglement is different. Entangled particles are not like pre-labeled gloves. They are like a pair of gloves that do not decide which hand they belong to until after you open a box, and whichever one you check first somehow tells the other how to behave instantly, regardless of distance. It is not only that the outcomes are correlated, it is that the properties do not seem to exist in a definite way until you measure one of them. Your act of measuring one instantly sets the stage for the other. That is entanglement, one of the strangest and most astonishing aspects of the quantum world. Here is the core idea. When two particles are produced together or interact in just the right way, they can become entangled, which means their quantum states are linked. Whatever happens to one is connected to what happens to the other, even after they are far apart. Suppose you create two entangled photons whose polarizations are undefined until measurement. One will end up vertical, one will end up right lace, the other horizontal. But they do not settle that assignment in advance. They remain in a shared superposition of all possibilities. The moment you measure one, its outcome becomes definite, and at that same moment, the other outcome becomes definite too. Instantly. No signal is sent, no delay, no opportunity to coordinate. If you measure in Paris and the partner photon is waiting in Tokyo, the universe updates both outcomes at once. Einstein famously called this spooky action at a distance. He did not like spookiness. He believed in locality, the idea that physical influences cannot jump instantly across space. In relativity, no information travels faster than light. The notion that two particles could coordinate outcomes with no time to communicate deeply troubled him. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a challenge to the completeness of quantum mechanics. If quantum theory allows such instantaneous coordination, they argued, then the theory must be missing hidden variables that quietly determine the outcomes from the start. For Einstein, the universe was supposed to be orderly, predictable, and local. Decades later, experiments weighed in. The hidden instructions never appeared. In the 1960s, John Bell devised a test in the form of mathematical inequalities that could separate quantum predictions from hidden variable stories. Again and again, experiments showed the same thing. Quantum mechanics was right. Entangled particles violate Bell's inequalities. They behave in ways no local hidden variable theory can reproduce. The results look random for each particle, yet they are perfectly correlated across distance. It is as if the particles share a private script, one that is unwritten until the curtain rises, and then they improvise together with uncanny timing. This does not mean we can use entanglement to send messages faster than light. That would break causality. Nature does not allow it. The outcomes you get when you measure are fundamentally random. You cannot control which result appears, so you cannot encode a message in it. The instant coordination is real, yet it cannot be harnessed for superluminal communication. Think of two people flipping coins in opposite galaxies. Each flip is random, but somehow, whenever one lands heads, the other lands tails. Neither flipper knows the result in advance or chooses it. They are not sending signals. They are simply connected in a way that ignores distance. Another unsettling feature is that entanglement does not fade with separation. Spread entangled partners across a room, a continent, or a light year, and the correlation survives. There is no known distance limit. Physicists have even distributed entanglement over hundreds of kilometers with satellites, and the results continue to match quantum theory. So what is entanglement? Is it a subtle tether? A shared identity stretched across space? A kind of information smeared between objects? No single answer has won the day. Some interpretations treat entanglement as a statement about what we know, rather than what is. Others see it as a sign that reality has a deep, non-local structure. There is even a bold idea that entanglement is not just a curious byproduct of space and time, but the scaffolding from which space and time themselves emerge. In that view, entanglement does not occur inside space. Entanglement stitches space together. Beyond philosophy, entanglement is practical. It powers quantum teleportation, which transfers quantum states from one location to another. It underlies quantum key distribution that promises secure communication. If an eavesdropper tries to grab the key, the entanglement is disturbed and the intrusion can be detected. In quantum computing, entanglement lets many qubits act together in ways that cannot be reduced to separate parts. That interconnection is part of the advantage. It is not just speed, it is a new kind of parallelism that classical machines cannot match. What once felt like spectral mischief has become the foundation of serious technology. Einstein may not have liked it, yet the mathematics remains consistent, and while relativity and quantum mechanics still await a unified home, each continues to work spectacularly well in its own domain. Entanglement reminds us that the universe is not merely a pile of separate objects. It is a web of relationships where distance sometimes misleads. We do not wake up entangled with our neighbors, and your morning coffee does not mirror a stranger's spoon. Yet at microscopic scales, This quiet partnership hums along everywhere all the time. Perhaps that is the strangest lesson of all. In a cosmos full of empty space and silent stars, there are still echoes of togetherness, instant, invisible, and remarkably real. Few animals in science are as famous as Schrödinger's cat. This hypothetical pet has become the unofficial mascot of quantum theory, a creature caught inside a thought experiment so peculiar that many assume it is pure satire. In a way, it is. It was never meant as a literal proposal. Like most strong metaphors, it reaches for something deeper, a quiet discomfort at quantum mechanics' core. The scene is the 1930s. Physicists agree that the equations work. The predictions line up with experiments. But what do the equations mean? Is the wave function a physical thing, or is it a calculator of expectations? Do particles truly exist in multiple states until someone measures them, or is that just bookkeeping? Erwin Schrödinger, already celebrated for the equation that bears his name, worried about how far some colleagues were pushing superposition and measurement. He found it suspicious to apply rules that govern electrons to ordinary objects, like, say, a cat. So he asked a question that was as dark as it was playful. What happens if you scale quantum weirdness up to something you could actually hold? Imagine a closed box. Inside sits a cat. Alongside the cat, you place a tiny radioactive atom, a Geiger counter, a vial of poison, and a mechanism that will break the vial if the detector clicks. If the atom decays, an outcome that is random according to quantum theory, the counter registers the event, the mechanism releases the poison, and the cat dies. Here is the twist. Quantum mechanics says that until you observe the atom, it exists in a superposition of decayed and not decayed. That logic spreads to the entire setup. Detector, mechanism, vial, and yes, the cat all join the superposition. The cat is both alive and dead, not figuratively, literally, at least in some interpretations. No one has put a living cat into a quantum box. Schrödinger was not proposing a real experiment. He was making a point. He found it absurd to treat a warm, whiskered animal with the same blur that describes electrons. The image caught on because it captures quantum indeterminacy in a single, unforgettable picture. A cat that is alive and dead until the lid opens. It is not about indecision. It is about possibility. Before you measure a system, it lives in a cloud of options. The wave function encodes them all. When you extract information, the cloud collapses. One outcome becomes real. The rest fall away. But what counts as a measurement? Is a conscious observer required? Does a mechanical detector suffice? Does the environment itself qualify? Different interpretations give different answers, and that uncertainty keeps the cat in the spotlight. The Copenhagen viewpoint advises restraint. The wave function tells us everything we can know, and measurement is where questions stop. Many worlds suggests the wave function never collapses at all. The cat is alive in one branch and dead in another, and opening the box selects which branch you occupy. Decoherence proposes that the environment continuously entangles with the system, washing out interference and leaving behind classical appearances. In that reading, the cat is not hovering in mystical limbo. The superposition is simply inaccessible because it is spread into countless environmental degrees of freedom. Every perspective has philosophical costs, but they all agree on one thing. Quantum systems are not miniature versions of classical objects. They do not wait passively to be discovered. They evolve probabilistically until an interaction singles out a result. Which brings us back to the cat. the box becomes a boundary between quantum and classical behavior, a small stage where common sense falters. Questions like, is the cat alive, refuse simple answers. The honest statement is that the cat is in a superposition of states until the box opens and the uncertainty collapses into a definite story. That is why the cat remains such a useful metaphor. In the quantum world, the Schrödinger equation guides evolution, yet it does not choose a single route. The system explores all paths at once. An electron does not march straight from A to B. It spreads across every possible course until a measurement reduces the blur to one outcome. The cat in the box is a large-scale version of that rule. The difference is scale, not principle. That is what worried Schrödinger. If the theory applies everywhere, then in some sense everything, including us, must be involved in superpositions. This leads to a final, gently unsettling question. What if the observer is part of the system? If opening the box collapses the cat's wave function, what collapses ours? Where does the chain of observers end? Are we just links in a long quantum procession, collapsing probabilities as we go? Or are we riding the wave, surfing a sea of possibilities? Never entirely sure where the next collapse will place us. In the end, Schrödinger's cat is not really about life and death. It is about knowledge, about the unusual dance between reality and observation. It is about what it means to declare that something exists when the declaration itself may change what happens. It reminds us that in the quantum realm, certainty is rare, clarity is conditional, and sometimes the universe waits patiently for us to lift the lid. Now back to the way particles move. In ordinary life, walls are simple. Throw a tennis ball at a wall without enough energy, and it bounces back. Predictable. The ball obeys classical rules. In the quantum realm, predictability loosens its tie. A particle can strike a barrier, lack the energy to cross, and still appear on the far side. No cracking, no squeezing through a gap. It simply shows up beyond the obstacle, as though the wall were not quite as solid as it looked. This is quantum tunneling. Tunneling is real, measurable, and essential to how the universe works. Probability is the key. Remember that in quantum mechanics, particles are described by wave functions that spread through space. Those waves do not end abruptly at obstacles. They fade gently. If there is a region that is classically off limits, a wave function can still seep into it, like a whisper passing through a wall. If the wall is not too thick or too tall, that whisper can make it out the other side. The particle may not have the energy to climb the barrier, yet its wave function can tunnel through, and with some chance, the particle will be found beyond it. If even a fragment of the wave function stretches across a barrier and survives on the other side, there's always a small, but never zero, chance that the particle itself will be discovered there as well. This isn't sorcery, it's mathematics. Although the idea sounds abstract, tunneling has very concrete and critical consequences, especially at atomic scales. Take radioactive decay. Some atomic nuclei are inherently unstable, and one way they reach stability is by releasing particles such as alpha particles, clusters made of 2 protons and 2 neutrons. Classically, these particles should remain trapped inside the nucleus, held in place by a powerful nuclear force barrier. They simply don't have enough energy to escape, and yet they escape constantly. Why? Because of quantum tunneling. Inside the nucleus, the alpha particle's wave function extends outward, brushing against the nuclear boundary. On rare occasions, the wave function slips through the barrier, giving the particle a chance to appear outside. The probability is small, but over time, it accumulates. Eventually, the particle pops free. That's radioactive decay in action. Without tunneling, many elements would remain frozen in place. Nuclear physics as we know it would grind to a stop. Tunneling also lies at the heart of the most important energy source in the cosmos: nuclear fusion. In stellar cores, hydrogen nuclei are crushed together by immense pressure and blistering heat. But even in those extreme conditions, the nuclei still lack enough energy to completely overcome the electrostatic repulsion between their positively charged protons. Classical calculations suggest fusion should be incredibly rare, yet stars burn brightly. Tunneling explains why. At those fiery temperatures, hydrogen nuclei approach each other closely enough for their wave functions to overlap. With each approach, there's a minuscule chance one nucleus will tunnel through the electrostatic wall and fuse with another. Multiply that tiny chance by the uncountable number of particles in a star, and you get a roaring fusion furnace, producing the light of suns and the explosions of supernovas. And tunneling isn't just a stellar phenomenon. We make use of it here on Earth, in research labs, in industrial devices, even in emerging technologies. One elegant example is the Scanning Tunneling Microscope, STM. This instrument lets scientists view surfaces with atomic precision. It works by positioning an ultrafine tip just a few nanometers above a material's surface. At such close distances, electrons can tunnel across the tiny gap between the tip and the surface. By measuring the tunneling current as the tip scans, the STM produces a map so detailed it reveals individual atoms. What's remarkable is that the microscope never physically touches the atoms. Its vision relies entirely on tunneling, on electrons slipping across empty space to create an image. This non-contact method has opened up entire landscapes of atomic detail, giving us a direct window into the quantum terrain beneath ordinary matter. Tunneling also drives certain electronic components, such as tunnel diodes and quantum dots. And as our computer transistors shrink smaller and smaller, tunneling increasingly intrudes. At nanoscales, electrons can tunnel through barriers that were once secure, like walls that have suddenly become permeable. This introduces both problems and opportunities. It can create noise and unpredictability in conventional electronics, but it also points the way toward technologies that harness tunneling instead of fighting it. At its deepest level, tunneling reveals something profound about the universe. We imagine the world as built from rigid boundaries. A particle belongs here, not there. A wall blocks passage, absolutely. But the quantum world is subtler. Its barriers are probabilistic, more like guidelines than laws. This fuzziness may feel unsettling, but it carries an elegance of its own. Because of tunneling, particles are not confined to the neat, linear paths of classical logic. They can cheat, blur, and take shortcuts. They remind us that the universe is less like a machine of perfect gears and more like a shimmering web of likelihoods. The tennis ball still bounces off the wall, but the electron, the alpha particle, or the photon might glance at the same wall and quietly decide, "I'll take the shortcut." And somehow, nature agrees. In everyday life, we treat nothing as truly nothing: an empty shelf, a blank page, the hollow beneath your bed where socks mysteriously vanish. In physics, the vacuum of space is often imagined as a perfect void, silent, cold, without a trace of matter or energy. But in quantum physics, nothingness is never empty. What we call the quantum vacuum is a restless stage, jittering with invisible activity. Even when no particles are present and no fields seem active, the vacuum still teems with energy. At microscopic scales, space hums. Waves rise and fall. Particles flicker into existence and vanish again. It is the faint glow behind darkness, the murmur beneath silence. All of this begins with uncertainty. Heisenberg's principle doesn't just bind position and momentum. It also links energy and time. That means even in a region where energy should vanish, it can briefly fluctuate. Out of those fluctuations appear virtual particles, particles that erupt into existence for fleeting moments before disappearing. They're called virtual, not because they're imaginary, but because they can't be directly observed. We infer them only through their effects, and their effects are real. One of the clearest demonstrations is the Casimir effect. Imagine placing two thin, perfectly conducting metal plates extremely close together in a vacuum. Classically, nothing should happen between them. But quantum theory predicts otherwise. Because of the narrow gap, only certain wavelengths of virtual particles can exist between the plates. Outside, all wavelengths are allowed. The imbalance produces slightly more pressure on the outside than on the inside, gently pushing the plates together. This Casimir force is small but measurable. In laboratory experiments, scientists have detected it exactly as quantum mechanics predicts. It's as if the vacuum itself reaches out to squeeze the plates. Vacuum energy doesn't stop there. On cosmological scales, it may explain one of the universe's greatest mysteries: the accelerating expansion of space. Dark energy, the unknown driver of this expansion, may be linked to the energy density of the vacuum. But there's a puzzle. Quantum field theory predicts an enormous vacuum energy, up to 120 orders of magnitude, greater than what astronomers observe. This mismatch has been called the worst prediction in all of physics. Solving it remains one of the field's great challenges. Even so, virtual particles leave their fingerprints everywhere. They affect the electromagnetic force, the stability of protons, even the tiny shifts in atomic energy levels. The famous Lamb shift in hydrogen atoms only made sense once physicists accounted for vacuum fluctuations. When we include these effects, theory and experiment align with breathtaking accuracy. In a sense, the quantum vacuum may be the most fundamental field of all. Every other force, electromagnetic, nuclear, gravitational, plays out against its background hum. Some physicists believe the vacuum may hold the key to deeper mysteries, perhaps even to the nature of space-time itself. It's humbling to realize that even nothing is alive with possibility. In the gaps between particles, in the silence between stars, something always stirs. Physics gives us the instruments to hear it. The vacuum hums, particles flicker, and reality itself dances to a rhythm we've barely begun to comprehend. In the quantum world, stories rarely have neat beginnings and endings. Particles don't travel in straight lines. They drift through clouds of probability, entangle, superpose, and tunnel their way through barriers. But perhaps the most mysterious twist arrives when we ask, what happens when we look? The act of observing seems to change everything. Before measurement, a particle is described by a wave function, a mathematical object containing every possibility of where it might be and what it might do. The electron is not here or there. It is both. Its spin is not up or down. It is both. Its path is not chosen. It is all paths at once. The wave function is a fog of probabilities. Then you measure. You switch on the detector. You ask, where is it? And instantly, the fog collapses. The possibilities snap into a single outcome. The electron appears in one exact spot. Its spin is up or down, but not both. And the collapse isn't gradual. It's abrupt. One moment, many possibilities. The next, one reality. This is wave function collapse, and no one truly understands what causes it. Is it the act of measurement itself? The transfer of information? Consciousness? A passing photon? We don't know. More than a century after quantum theory was born, collapse remains one of its biggest mysteries. Different interpretations try to explain it. The Copenhagen view, championed by Niels Bohr and Werner Heisenberg, treats the wave function as a predictive tool, not a physical thing. Collapse happens when information is gained. Asking what really happens in between isn't meaningful. The many worlds interpretation rejects collapse altogether. It proposes that all possibilities unfold, each in its own branch of the universe. Measure a spin, and reality splits. One universe for up, one for down. Collapse is replaced with branching. Objective collapse theories say the wave function is real and collapses spontaneously, sometimes triggered by measurement, sometimes randomly. Decoherence offers another explanation, describing how interaction with the environment washes away interference and makes systems look classical. And then there are more radical views, like cubism, which suggests the wave function isn't about the system at all, but about our beliefs. Collapse isn't a physical event. It's an update in our knowledge. Each perspective is compelling in its way, and each carries philosophical consequences. None has settled the debate, but all remind us that measurement is not a trivial act. It is a moment when probability yields to presence. You might think of collapse as a phase change, like water freezing into ice. But unlike water, collapse isn't something we can see or touch. It exists in the realm of possibilities. We don't know the rules, no temperature, no pressure, just a fog turning into form when looked at. Perhaps the real collapse is not of the wave function, but of our assumption that the world must always be definite. Maybe the universe itself is content with indecision, and we are the ones who demand closure. Which brings us to Copenhagen itself. If quantum mechanics had a hometown, it would be there, not because of the canals or bicycles, but because it was in Copenhagen where the strangest ideas of physics were first shaped, argued, and tentatively embraced. At the center of that gathering was Niels Bohr, the Danish physicist with gentle mannerisms and famously long, complex sentences. Bohr gave shape to one of the most influential perspectives in physics, the Copenhagen interpretation. In the Copenhagen picture, a quantum system does not carry definite properties until it is measured. Before you look, an electron has no fixed location. A photon has not settled on a particular polarization. A particle has not chosen a specific state. Only when an observation is made does the system commit. Prior to measurement, reality is a hazy field of possibilities, a probability wave rather than a set of hard facts. A reading does not simply uncover what was already there. It brings a single outcome into being. Put differently, reality is not fully real until we ask it to be. That statement is bold. It is the sort of idea that makes philosophers sit straighter and sends physicists toward the coffee pot. Still, Niels Bohr and his colleagues were not trying to manufacture mystery. They were trying to make sense of experiments. Each time they treated particles like tiny billiard balls with definite properties at all times, the mathematics failed. When they treated particles as probability waves that only resolve at the moment of measurement, the numbers lined up and the confusion eased. In this view, the wave function is not a physical object. It does not describe where a particle actually is or how fast it is truly moving. It encodes what can be known about the system. Think of it as a mathematical catalog of possibilities, rather than a literal map of what exists. From here follows a central claim of Copenhagen. Questions about a system's state before a measurement do not carry meaning. Asking where the electron was a moment before you measured it is a broken question, because the notion of where only becomes meaningful after a measurement has taken place. Reality is not a curtain to be peeled back. It is something that snaps into focus the moment you look. It is not that the particle was disguising its true nature. It simply did not have one yet. Not everyone found this satisfying. Albert Einstein, especially, was uneasy. He wanted a universe that existed in a clear way, whether or not anyone was watching. He believed in an underlying reality that was objective and deterministic, even if it remained hidden for now. To him, Copenhagen sounded dangerously close to saying that the moon does not exist unless a person is gazing at it. Bohr disagreed, and he did not try to supply a grand metaphysical cure. He embraced a pragmatic kind of ambiguity. Quantum theory, he argued, tells us what we can say about nature, not necessarily what nature is. In this framing, the role of physics is to make precise statements about experiment, not to claim a final description of what lies underneath. If that sounds unsatisfying, you have company. Critics often say Copenhagen is more of a prescription than a description. It tells you how to use the equations and what outcomes to expect, but it keeps quiet about the machinery behind the curtain. This attitude gave rise to a famous bit of gallows humor: shut up and calculate. Bohr did not coin the line, yet it captures the mood of many working physicists. Stop worrying about metaphysics and run the numbers. The predictions work. Is that not enough? To be fair, the Copenhagen approach does work. It is the default stance in textbooks, classrooms, and countless laboratories. It underlies the design of semiconductors, lasers, and many quantum devices. It has never failed an experimental test. For many researchers, that record outweighs philosophical discomfort. Even so, the itch remains. If reality only becomes definite when measured, what about the time before observers existed? Did the early universe lack definite properties until someone appeared? Most physicists answer no. Copenhagen does not require conscious minds. It requires an interaction that extracts information, which can be a measuring device or even the surrounding environment. In this usage, observation is any process that forces a quantum system to pick a side. Yet that raises further questions. What exactly counts as a measurement? At what point does the wave function collapse? Why does the universe follow this strange rule? The Copenhagen camp tends to answer, with a small smile, that the theory does not explain why collapse happens. It only tells you when to apply the rule. If you want a deeper mechanism, you must look to other interpretations. Many have tried. Competing ideas such as many worlds, pilot wave theory, and objective collapse models aim for a more complete picture. Each tries to keep some classical intuition alive, such as an observer-independent reality or a clear chain from cause to effect. Each comes with its own price. Copenhagen, in contrast, stays lean. No hidden variables, no multiplying of universes, just a short rulebook. Compute the wave function, apply the measurement postulate, predict outcomes. Simple, direct, effective. Perhaps that is why it continues to appeal. In a field full of strange possibilities, Copenhagen offers a quiet steadiness. It is not trying to solve every riddle. It is content to describe what we can see and measure without claiming to know the deeper machinery. Maybe that is enough. Bohr often spoke in layered, almost poetic sentences. He once said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." He knew that Copenhagen was not about making peace with reality. It was about making peace with uncertainty. Quantum theory is weird. Rather than force it into a tidy shape, Copenhagen invites us to accept the weirdness and work within it, without demanding that the universe explain itself. It is not a final answer. It is a quiet set of instructions, a reminder that in the quantum world simplicity and discomfort often travel together. and that sometimes the wisest thing is to stop arguing and calculate. Now picture a coin between your fingers. You flip it. It spins in the light, lands with a gentle clink, and shows heads. According to another interpretation of quantum mechanics, something else happened too. Somewhere, still real but not here, the same coin landed tails. Somewhere else, it balanced on its edge, rolled away, and slid beneath the couch. Every possible outcome of the flip unfolded, not as a mere chance, but as an actual branch of reality. You find yourself in the branch that saw heads. This is the strange and elegant idea called the many worlds interpretation. It began as an alternative way to think about the notorious collapse of the wave function. Remember that the wave function is the mathematical cloud of possibilities that describes a quantum system. In the traditional Copenhagen approach, a measurement collapses that cloud into one outcome. Many worlds asks a different question. What if the wave function never collapses at all? In 1957, the physicist Hugh Everett III proposed a radical answer. Perhaps the wave function always evolves smoothly and deterministically. In that case, when you measure a system, you do not force it to choose a single result. Instead, the world splits. The measuring apparatus, the system, and you separate into distinct, correlated branches. Every possible outcome occurs, each in its own branch. It sounds like science fiction, but Everett was not writing a story. He was following the mathematics, which remains identical to standard quantum theory if you remove the extra rule that says collapse happens during observation. Consider an electron with two possible spin states, up and down. Classical quantum mechanics says the electron is in a superposition until measured. Then it chooses. Everett says there is no need for a choice. The measurement entangles you with the electron, and the combined system branches. In one branch, you see spin up. In another, you see spin down. Both outcomes are real. Both versions of you exist, each unaware of the other. This can sound like a recipe for a noisy multiverse packed with doppelgangers. Yet many worlds does not add new forces or new particles. Its appeal is that it keeps the math simple and removes the rule that something special happens when you look. For supporters, that is the strength. The idea is certainly odd, but the equations are clean. There are objections. If the universe is branching constantly, what becomes of all those branches? Are they stacked in a higher space? The interpretation does not specify. It is not a theory of the architecture of space. It is a statement about how quantum states evolve. The branches are real, but once they decohere, they do not interact. They become effectively invisible. That makes direct tests difficult. If you cannot observe the other branches, how do you know they exist? Critics ask whether the idea is falsifiable. Fans reply that this is the wrong test. Many worlds does not aim for new predictions. It aims to avoid extra assumptions. If the Schrödinger equation never includes collapse, why add collapse? Occam's razor is tricky here. Copenhagen keeps the number of worlds small by adding the collapse rule. Many worlds keeps the mathematics minimal by accepting a very large reality. Which simplicity do you prefer? The scale is worth a breath. Quantum interactions branch the universe continually, not just in the laboratory, but in every photon emission, every molecular collision, every atomic decay. Yet, we do not feel the branching, just as we do not feel the planet turning beneath our feet. We simply experience one outcome as if it were the only one. It is also important to clear away a common picture. In many worlds, you do not hop between branches or meet other versions of yourself. The branches are causally isolated. No messages travel across the divide. Once a split happens, it is permanent. This framework smooths away several headaches. You no longer need to define what counts as a measurement or when reality becomes definite. Everything evolves continuously. Measurement is just entanglement that correlates system and observer. There is still a cost. If every outcome occurs, why do we feel as though one outcome happened? What becomes of probability? In many worlds, probability is reinterpreted. It is not the chance that a single world will obtain a result, but a measure of how much of you ends up in each branch. That shift is subtle and not intuitive, though quantum theory rarely is. Despite its strangeness, many worlds continues to inspire serious work. Some researchers think it could help with unifying quantum theory and gravity. Others see a natural harmony with quantum computing, where superposition and entanglement let information processing spread across many possibilities at once. It also offers a peculiar comfort, or a chill, depending on your mood. In this view, no outcome vanishes entirely. Every possibility exists somewhere. Choices not taken and paths not walked still unfold in other branches. It is not meant to make you feel small. It suggests that reality may be more generous than we imagined. Not a single thread, but a great branching tree. So when you picture many worlds, do not imagine a noisy stack of cartoon timelines. Imagine a quiet tree, each twig a path, each leaf a world, each outcome a small poem in the language of physics. All of them, in their own way, true. Now pull back the curtain on everything you can see. The stars, the ocean, the chair, your hand, the soft light resting on your pillow. What if all of this is not built from hard bits at all? What if the deepest stuff of reality is not stuff, but vibrations, waves, tiny ripples that spread through fields filling all of space? Welcome to quantum field theory, a gentle but profound shift in perspective, where the universe is not built out of particles first, but out of fields that shimmer beneath everything. Begin with a classical idea. A field assigns a value to every point in space. The electric field is a familiar example. It is an unseen influence that tells a charged object how it should move. Place a positive charge inside an electric field, and it feels a push. Fields are smooth and continuous, filling space like an invisible jelly. Quantum mechanics adds a new ingredient. Fields do not sit quietly. They fluctuate. They buzz even when no ordinary particles are present. Every field, whether electric, magnetic, or gravitational, is quantum in nature. Even the vacuum is not calm. It has a restless pulse. Here is the key step. In quantum field theory, everything is a field. Every particle you have heard about is a local ripple, a quantized wiggle in the matching field. An electron is not a marble. It is a localized excitation of the electron field. A photon is not a bullet. It is a tiny vibration in the electromagnetic field. Adjust the vibration and you see visible light, or microwaves, or X-rays. Different notes, same instrument. There is a field for every known particle. Quark fields, gluon fields, the Higgs field. If a graviton exists, it would be a ripple in a gravitational field. In this viewpoint, particle is a useful label for a certain behavior of the field. The field is fundamental. The ripple is what we notice. This shift is profound. It changes the universe from a Lego set made of bricks into a symphony where overlapping notes and harmonies produce the world we experience. Quantum field theory also clarifies puzzles that older quantum pictures found awkward. Particles appear and vanish in high-energy collisions because energy poured into a region can excite a field strongly enough to produce new ripples. That is how accelerators create new particles. Antiparticles fit neatly as excitations with opposite properties in the same field. Forces are field stories, too. The electromagnetic force is captured by exchanges of photons, which are ripples of the electromagnetic field. The strong force binds quarks by exchanging gluons, which are ripples of the gluon field. Gravity, if successfully quantized, would involve tiny ripples in a gravitational field. Even empty space has a say. Fields never become perfectly still. They jitter with vacuum fluctuations, producing real effects, such as the Casimir attraction between closely spaced metal plates. There is a calm beauty here. Space is not a stage waiting for actors. It is an active participant. Every point is alive with possibility. Every particle and every force is the field expressing itself. Of course, quantum field theory is not simple to master. The mathematics is intricate and the symphony is dense. Yet the picture it offers is gentle. Reality is an ocean of fields. Particles are small traveling ripples. Interactions are patterns of waves meeting and reshaping each other. What seems like hard matter is music, and the score is written in the quiet symbols of quantum fields. You can't exactly work this out on the back of a napkin, unless that napkin is the size of a lecture hall blackboard, and you're armed with chalk-marked Feynman diagrams. But the essence is surprisingly elegant. At its deepest level, nature isn't composed of tangible things. It's built from excitations, oscillations, and energy woven through space and time. Even the property we call mass, the heaviness that gives matter its stubborn weight, isn't always fundamental. In many cases, it emerges from field interactions. Take the Higgs field, discovered experimentally in 2012. This invisible field stretches across the universe, and particles interact with it much like swimmers slogging through syrup. The more strongly a particle interacts with the Higgs field, the greater its mass appears. The field resists, and that resistance manifests as weight. So here we are, living inside a cosmos of fields. As you listen to these words, you yourself are a fragile but intricate pattern etched in the electron field, the quark field, the photon field. Your very thoughts are excitations, little ripples rippling across fields. The atoms that make up your body aren't isolated marbles, but intersections in an enormous web of vibrating fields, all resonating together in hidden harmony. You don't really stop at the edge of your skin. The fields that make you extend outward, blending seamlessly into the wider universe. There is no hard line between you and not you, just ripples fading into the great ocean of quantum reality. Quantum field theory doesn't just describe the universe. It is, in many respects, the universe. Or at least, the most accurate map we have drawn so far. It's a picture of reality, not as billiard balls colliding, but as fields dancing in an endlessly subtle, endlessly beautiful choreography, too swift and too delicate to ever fully capture. And if you're still awake, perhaps you're wondering, if everything is a ripple in a field, then what are the fields themselves rippling through? That, dear listener, is a question best saved for another dream. If the universe came with a recipe book, the standard model of particle physics would be its ingredient list, though it leaves out a few mysterious spices like dark matter and dark energy. Surprisingly, this recipe is compact. Its structure is tidy, though its naming conventions sometimes veer into chaos. For all its quirks, the Standard Model is one of the most astonishingly successful frameworks in all of science. It lays out what the universe is made of, how those parts interact, and why the cosmos behaves the way it does. At its core, the Standard Model introduces us to the cast of elementary particles, entities that, as far as we can tell, cannot be broken down into smaller parts. They are the indivisible building blocks of matter and the carriers of forces, all stitched together by quantum fields. There are three broad families: quarks, leptons, and bosons. Quarks are the raw material of protons and neutrons, the sturdy cores of atoms. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Yes, those are their real names. Physicists can write mathematics with dizzying precision, but when it comes to naming, whimsy prevails. The up and down quarks are the most common. A proton is composed of 2 ups and 1 down, a neutron of 2 downs and 1 up, which means nearly everything around you, and you yourself, is built from ups, downs, and electrons. The other 4 quarks, charm, strange, top, and bottom, are heavier, short-lived, and typically appear only in extreme environments like cosmic rays or particle accelerators. They're like cameo stars in the quantum story, flashy, rare, but crucial. Then there are the leptons. You already know the electron, whizzing around atoms and carrying electricity. But the electron has heavier siblings, the muon and the tau. They're like heavyweight versions of the electron, appearing briefly in high-energy events before decaying away. Each of these charged leptons comes paired with a neutral partner, the neutrino. There are 3 neutrinos: electron, muon, and tau neutrinos. They are nearly massless, travel at close to light speed, and interact so weakly with matter that billions pass through your body each second without leaving a trace. They're the wallflowers of the cosmos, always present, rarely acknowledged. So far, that's 6 quarks and 6 leptons, arranged neatly into 3 generations. That gives us 12 matter particles in total. But matter alone doesn't run the universe. We need forces, and that's where bosons come in. Bosons are the messengers of the fundamental forces. They're the carriers of interaction, the quantum handshakes between particles. For electromagnetism, the carrier is the photon, the particle of light. It's massless, travels at the speed of light, and binds electrons to atoms. Without photons, chemistry and breakfast wouldn't exist. The weak nuclear force, which governs radioactive decay, is carried by the W+, W-, and Z bosons. Unlike photons, they are extremely heavy, which limits their reach. Yet they're critical. They allow neutrons to transform into protons, driving the nuclear fusion that powers stars. The strong nuclear force, which binds quarks together into protons and neutrons, relies on gluons. There are 8 types of gluons, massless but wildly energetic, constantly exchanging between quarks like an excitable group of toddlers in a ball pit. They're the reason your atoms don't fall apart. And then there's the newest member of the family, the Higgs boson. Confirmed at CERN in 2012, it's the tangible ripple of the Higgs field, the field that endows many particles with mass. Without it, most particles would be massless wisps, unable to cluster into atoms. So, to recap, the Standard Model contains 12 matter particles, 6 quarks, 6 leptons, and 5 bosons: photon, W, Z, gluon, and Higgs. Together, They form a model that has withstood decades of testing. Its predictions match experiments with uncanny accuracy, from particle collider data to radioactive decay rates. But it's not flawless. It leaves out gravity, which is still governed by Einstein's general relativity. It has no explanation for dark matter or dark energy, which make up most of the cosmos. In fact, the standard model accounts for only about 5% of the universe. Still, that 5% is everything we see, touch, and breathe. Think of it like finishing a puzzle, only to realize the picture on the box is just a corner of something far larger. Yet even that corner is dazzling. Intricate symmetries, precise relationships, and mathematical beauty that hint at deeper truths still hidden. When asked what the universe is made of, you can say with a smile, mostly quarks, a few leptons, and a handful of bosons. And for flair, add, oh, and the Higgs field. Without it, none of this would have any weight. Hovering above this sits a glittering jewel of physics, quantum electrodynamics, QED. This theory explains how light and matter interact, and does so with such precision that even the pickiest decimals line up in awe. At its essence, QED describes the quantum relationship between electrons and photons. Every flicker of light, every spark, every electromagnetic nudge, it all flows from the laws of QED. Despite involving an infinity of possible interactions, its predictions match experiments to a staggering degree, better than 1 part in a billion. That's like measuring the width of North America to within a human hair and getting it right. The problem QED solved was daunting. Early in the 20th century, scientists knew electrons interacted with electromagnetic fields. But when they tried to calculate those interactions quantum mechanically, the equations misbehaved. They spat out infinities, nonsensical results like infinite energy. Enter Richard Feynman with his quick wit, love of bongo drums, and genius for clarity. Along with Julian Schwinger and Sin-Itaro Tominaga, he found a way to tame the theory. Feynman's special contribution was a visual language, Feynman diagrams. These simple sketches turned nightmarishly complex math into intuitive doodles. Lines represented particles. Time moved left to right. An electron might emit a photon, absorb one, or interact through loops of virtual particles, entities that exist briefly in the math but affect real outcomes. The trick of QED is that it doesn't just consider the most likely path. It considers every possible path. An electron may zig, zag, loop, or detour. Each path has a mathematical weight. Add them all together, and you get predictions that match experiments with astounding precision. One of its crowning achievements is explaining the electron's anomalous magnetic moment, a tiny tweak in its magnetic strength caused by quantum effects. QED predicts this tweak to more than 10 decimal places, and experiments confirm it exactly. QED also explains phenomena like Compton scattering, photons bouncing off electrons, brims straddling, radiation emitted when particles slow down, and pair production, light transforming into matter and antimatter. Each falls naturally out of the QED framework, as if the equations were quietly writing poetry in calculus. And QED isn't just important in itself. It's the prototype for other quantum field theories, quantum chromodynamics, QCD for the strong force, electroweak theory for the weak force, and more. QED came first, and it set the standard. Feynman himself joked that the rules of QED could be scribbled on the back of a napkin. Particles explore every path, each with a probability amplitude. Square the sum, and you get the probability of what happens. Simple to state, maddening to calculate. Yet out of this framework comes one of the most accurate scientific theories ever built. Within its domain, QED reigns supreme. It doesn't explain gravity or dark matter, but where it applies, no rival comes close. It is the most rigorously tested theory in science's history. Feynman often warned that nature always has more secrets to reveal. But even he admitted that QED was something extraordinary. It's humbling to think. This quiet mathematical machinery choreographs everything from the glow of your bedside lamp to the shine of distant stars. QED is the heartbeat of light and matter, a whisper that shapes the universe billions of times per second, always in perfect time. And now, on this foundation, humanity dares to build something futuristic: quantum computing. If classical computers are like well-trained librarians, orderly and efficient, quantum computers are more like strange poets. They don't just read books one at a time. They hold many open at once, whispering overlapping verses, and somehow still manage to produce coherent answers. At the center of this is the qubit. Classical computers process bits, zeros and ones, like switches flipped off or on. But a qubit can exist in superposition, a blend of both 0 and 1 simultaneously. Think of a spinning coin. Until you stop it, it's not heads or tails, but both. A single qubit can represent multiple states at once. And as you add more qubits, the power grows exponentially. 2 qubits can hold 4 combinations. 3 can hold 8. 20 can hold over 1,000,000. With enough qubits, a quantum computer can explore astronomical numbers of possibilities in parallel. But superposition is only half the magic. The other half is entanglement. When qubits are entangled, their states become linked. Change one, and the other changes instantly, no matter how far apart they are. This correlation allows quantum computers to perform operations beyond the reach of classical machines. For specific tasks, like simulating molecules, optimizing complex systems, or factoring enormous numbers, quantum computers promise immense speedups. But let's pause. Quantum computers are not about to replace your laptop. They're not general-purpose machines for editing videos or checking email. They are specialized tools designed to solve problems that classical computers would struggle with for centuries. In practice, building and operating a quantum computer is genuinely difficult. Qubits are astonishingly fragile. Tiny vibrations can disturb them. Minuscule temperature changes can knock them off balance. Even faint magnetic fields can push them out of alignment. Preserving a qubit's coherence, its ability to remain in superposition and maintain entanglement, demands exquisite care. Many hardware platforms must be cooled to temperatures hovering near absolute zero. That is colder than deep space. Then there is the matter of error correction. In a classical machine, if a bit flips by accident, we can detect and fix it with straightforward methods. In quantum hardware, the task is far trickier. You cannot simply copy the full state of a qubit without disturbing it, thanks to the no-cloning theorem. As a result, researchers have devised clever coding schemes that spread information across many physical qubits in order to protect a single logical qubit. Think of it like wrapping a whispering poet in layers of soundproofing, so the poem can continue uninterrupted by the noisy world. Despite these hurdles, progress has been real and rapid. Companies and laboratories have built processors with tens to hundreds of qubits. Several groups have showcased forms of quantum advantage, sometimes called quantum supremacy, by performing tasks that a classical computer would take an impractical time to finish. Others are pushing forward with NISQ devices, noisy intermediate-scale quantum, exploring what is possible with imperfect yet useful machines. There are already promising application areas under active study. One bright frontier is quantum chemistry. Simulating molecules at full quantum fidelity stretches classical computers to their limits. Quantum processors are naturally suited to this domain, which could reshape materials science, accelerate drug discovery, and push battery technology forward. Another fertile area is optimization. Problems with many competing constraints, such as routing fleets, scheduling limited resources, or designing resilient networks. Quantum algorithms may navigate these landscapes more efficiently, shaping probability so that good answers rise to the surface with fewer steps. Security is changing too. Algorithms like Shor's could, in principle, factor large numbers dramatically faster than classical methods, which would threaten widely used public key cryptography. This risk has sparked a new subfield called post-quantum cryptography, where researchers craft schemes designed to resist both classical and quantum attacks. Standards work is ongoing so that our digital infrastructure can remain secure in a quantum future. We should admit where we are. These are early days. Most current devices are noisy and delicate, and their computational reach is limited. The dream of a large-scale, fault-tolerant quantum computer remains years, perhaps decades away. Yet the journey is thrilling in its own right. Quantum computing takes the strangest features of quantum mechanics and turns them into tools. Superposition, once a philosophical curiosity, becomes a resource. Entanglement, once spooky, becomes practical. Even measurement, that act which collapses possibilities into a single outcome, becomes a step in a calculation. There is poetry in that. The very weirdness that once unsettled us is now harnessed to tackle problems previously thought unreachable. It is like taming a wild wind, not by resisting it, but by trimming a sail to catch it. Quantum computation invites us to rethink what it means to compute. It blurs the line between certainty and probability, between crisp logic and soft possibility. It reminds us that beneath the familiar surface of classical reality lies a stranger terrain where information is supple and intertwined, and answers emerge from orchestrated patterns rather than single tracks. We do not yet know where this road will lead. The walk itself, quiet and intricate and full of potential, is already redrawing what machines and minds may accomplish. We expect quantum physics to be odd. Particles tunnel through barriers, carry spins in two directions at once, and pair up in entanglement that appears to coordinate across vast distances. There is one realm we do not usually expect to find quantum behavior: biology. Life is warm, wet, and noisy. Cells bustle, molecules jostle, energy fluctuates. Quantum effects are famously fragile, fading quickly in the presence of heat and chaos. That is why we chill quantum chips to near absolute zero and oscillate experiments in high vacuum. And yet, life seems to play its own quantum games. Consider the robin, a modest bird with a remarkable sense of direction. Robins migrate thousands of miles with striking accuracy. How do they know where north lies? The suspicion of a biological compass is old. The proposed mechanism is newer and rather audacious. quantum entanglement might be involved. The hypothesis works like this. In a protein in the bird's eye, likely cryptochrome, a pair of electrons can be created in a quantum-linked state. When light activates the molecule, the electrons become entangled, and their coupled spins interact with Earth's magnetic field. That interaction shifts the course of a chemical reaction in a way that depends on the direction the bird is facing, effectively providing a magnetic sense. It sounds like science fiction. Entanglement is delicate. Could it persist inside a living cell swarming with water and proteins? Early evidence suggests it might. Experiments point toward a real quantum contribution to magnetoreception in birds. The story is not complete, but the signs are increasingly persuasive. If true, nature has discovered how to protect quantum information in a warm biological setting that human engineers still struggle to manage. Plants may be quantum strategists as well. Photosynthesis converts sunlight into chemical energy with startling efficiency. The standard picture says a photon's energy hops from molecule to molecule until reaching a reaction center. Measurements hint at something more elegant. The energy appears to explore multiple routes at once, using quantum coherence to find an efficient path. Imagine a marble released into a maze that spreads like a wave, sampling all corridors, then settling on the shortest route. Some photosynthetic complexes seem to behave in just that way. Coherence persists long enough on picosecond scales to influence the outcome, even in warm, noisy, cellular environments. If evolution has found a way to exploit quantum effects, it would not be surprising. Nature has had billions of years to experiment. Organisms that used quantum shortcuts for navigation, energy flow, or sensing could gain an edge and pass those advantages along. Smell may carry a quantum note as well. The usual explanation is lock and key. An odorant's shape fits a receptor in your nose. Yet there are puzzles. Different shapes can smell alike. Similar shapes can smell different. An alternative is the vibrational theory of olfaction. In this view, when a molecule binds a receptor, electrons in the receptor can tunnel through the molecule, with the tunneling probability depending on the molecule's vibrational frequencies. If so, part of smell would rely on quantum tunneling. Experiments with people, and even fruit flies, have shown cases where organisms distinguish between molecules that differ only in vibrational signature. The evidence is not definitive, yet it is intriguing enough to keep the debate alive. Quantum biology is young. Many proposals remain tentative. What makes the field exciting is not just novelty, but the reminder that quantum rules do not stop at the lab bench. They extend into feathers, leaves, and breath. The same equations that describe electrons in a vacuum also touch the robin's compass and the sunlight shimmering through a leaf. Nature does not draw hard borders around its domains. Quantum effects are not locked in a microscopic vault. They are woven into life. As we learn these tricks, we may gain new technologies and a deeper appreciation for the inventiveness of evolution. Life may have been playing with these strange tools from the start. Zoom back to the foundations. At the quantum level, particles spread into superpositions, interfere with themselves, and occupy many possibilities at once. Yet your daily world feels solid. You hold a mug. You sit at a desk. Your cat is alive, or not both. Why? Why are there no tables smeared across the room until you look? Why does your sandwich not exist as a probability cloud that collapses only when you open the refrigerator? The answer rests in a quiet process called decoherence. It explains how quantum behavior loses its delicate coherence, and yields the classical world we know. Picture a lone electron in superposition. Left alone in an ideal vacuum, it keeps its haunting quantum character. Back on Earth, isolation is rare. Air molecules rush. Photons scatter. Vibrations tremble through matter. The moment your quantum system interacts with this environment, its clean interference patterns begin to blur. That is decoherence. The superposition does not vanish in principle. Instead, the system becomes entangled with the environment, dragging a vast number of external degrees of freedom into the story. Once that happens, the system ceases to behave like a tidy, isolated wave and starts to behave like something ordinary. Privacy is lost, not because a conscious observer made a measurement, but because nature is always nudging and jostling. Air, light, and thermal motion act like a background of countless tiny observers. They do not collapse the state directly. They wash out the coherence that would allow interference to show up. Decoherence is gradual rather than abrupt. It does not need a grand apparatus. It needs time and contact. For small systems, we can isolate the environment and watch quantum effects endure. For macroscopic objects, decoherence is blindingly fast. The more complex and massive the object, the shorter the coherence time. For large items, the timescale can be a trillionth of a second or less. That is why your shoes do not sit in a quantum blur. Interaction with the world has already forced them into a definite state. In this sense, decoherence hides superpositions. They still exist within the full quantum description, but the entanglement with the environment makes the interference inaccessible. The result looks classical. This perspective helps with an old puzzle. How do probabilities become outcomes? Decoherence does not choose a specific result. It does explain why interference is not seen in large systems and why Schrödinger's cat is not both alive and dead on your counter. The environment has soaked up the delicate phase information, creating the appearance of collapse. Classical physics survives as an excellent approximation. We build bridges, guide spacecraft, and bake soufflés with it. Underneath, everything hums to quantum rhythms. Decoherence creates a veneer, a frozen surface over a liquid depth. One way to picture it: you walk on a frozen lake. Beneath the ice is water, shifting and fluid. Decoherence is the freeze that makes your footing reliable, while the water beneath continues to flow out of reach. There are practical implications. Quantum computers must fight decoherence constantly. Their qubits need quiet. A small vibration or a trace of heat can erase the advantage. That is why we keep them ultra-cold and shielded. Without that, the quantum benefit disappears. Decoherence also shapes interpretations. Some approaches argue there is no separate wave function collapse. Instead, once entangled with the environment, alternatives become unobservable. The tree falls, yet its delicate echo dissolves in the noise. Decoherence is not a universal solvent. It does not tell us why one outcome rather than another occurs. It does not resolve whether the wave function is a real physical entity or a tool. It does show how the quantum gives rise to the classical. The world you touch is not separate from the quantum world. It is molded by it through a continual exchange with everything around it. Each time you grasp a mug or turn a knob, decoherence is there, converting a universe of maybes into the firm handshake of a single result. Quiet, no sparks, no fanfare, just the graceful thinning of possibility into pattern. Now imagine an experiment so delicate that the timing of your choice to measure seems to reach backward and influence what already happened. It sounds like fiction or confusion, yet this is what you find in a family of experiments that probe cause and effect at their roots. They are known as delayed choice and quantum eraser experiments. If you hoped quantum physics would finally settle into common sense, this is where even time begins to shrug. Start with something familiar: the double-slit setup. Send photons, electrons, or even large molecules toward two slits, with a screen behind to record arrivals. If you do not check which slit a particle takes, you see an interference pattern, as if each particle traveled through both openings and interfered with itself. If you do install path detectors, the interference disappears. The particles behave like little bullets. Knowing the path destroys the wave-like behavior. Now add a twist. In the delayed choice experiment, first set up the system without measuring the path. Then wait until after the particle has passed the slits to decide whether to check which path it took. You delay your decision. Will you be the nosy detective, or will you let the particle remain ambiguous? The surprise is this: the pattern on the screen matches your later choice. Even though your decision comes after the particle has supposedly committed, the results line up with what you eventually do. Wave-like interference if you decline to check. Particle-like dots if you decide to measure. It is as if your future choice influences the earlier behavior. This suggests that the quantum world avoids committing until it must. The act of observation determines outcomes not only in space, but in a sense across time. Measurement appears to sculpt the story that the system will tell, deciding whether it reads as a wave narrative or a particle narrative. And then, of course, physicists ask the next question: how strange can this get? Now, let's meet the quantum eraser. In this twist on the classic double-slit experiment, you deliberately mark the particles so their paths could, in principle, be known. But then, using an ingenious technique, you erase that path information after the particles have already been detected. And when you do this, the interference pattern reappears. The particles resume behaving like waves, as though uncertainty itself had been restored retroactively, as though they had never surrendered their ghostly ambiguity in the first place. This introduces a deeply disconcerting thought. Perhaps reality isn't sealed and finalized until all potential information is resolved. Not only at the moment of detection, but also at the moment when decisions are made about what to do with that information. It's like a cosmic retelling of Schrödinger's cat, but stretched through time itself. Not only is the cat alive and dead simultaneously, but whether it was one or the other depends on a choice made after the box has already been opened. So what does this mean? One tempting interpretation is that information, not matter, is the true currency of the cosmos. In this view, quantum outcomes don't solidify until questions are asked in a way that forces definite answers. Until then, everything remains suspended, tangled together in a misty soup of probabilities. This doesn't imply that time travel is real or that we can rewrite the past. Rather, it suggests that our everyday picture of time as a tidy one-way flow may not apply in the quantum domain. Events in this realm aren't strung together by neat, linear chains of cause and effect. Instead, they belong to a strange holistic web in which outcomes only emerge when the system is considered as a whole. Still, boundaries exist. These experiments, however astonishing, don't permit communication with the past. You can't send messages backward through time or rewrite what has already happened. At the large-scale classical level, the results remain faithful to causality. But beneath the surface, those familiar rules are more pliable than we imagined. Some physicists frame this in terms of entanglement and correlation rather than causation. The particle isn't peeking into your future decisions. Instead, all parts of the experimental setup are linked in such a way that your eventual configuration determines which patterns appear. Others favor the block universe view, where all moments of time coexist simultaneously, like frames of a film reel. In that perspective, your later choice doesn't ripple backward. It was always embedded in the timeless quantum script. And then, of course, there are those who simply shrug and say, "Shut up and calculate." The essential lesson is this: the universe has no obligation to fit neatly within our everyday intuitions of time, cause, or measurement. Our classical instincts were built for tables, rocks, and coffee mugs, not for the subtle haze of quantum probabilities. In that haze, rules become softer, less linear, less local, and undeniably stranger. The delayed choice and quantum eraser experiments don't break physics. Instead, they reveal its richness. They show us that the quantum domain isn't a miniature version of our ordinary world. It's something profoundly different, governed by a logic all its own. So if time ever seems to play tricks on you, take comfort in knowing that at the quantum level, it very likely does. Now imagine zooming all the way into the very core of existence, past the spiral arms of galaxies, beyond molecules, beneath the atoms themselves. You would eventually reach a domain where certainty slips like sand through your fingers. Here, outcomes are not predetermined, but described only in terms of probabilities. Particles have no definite positions until observed, and even then, their placement is the result of a cosmic dice roll. Welcome to the quantum universe, not just small, but inherently uncertain. At its core, quantum theory suggests that randomness is not just present, but fundamental. This idea was unsettling enough to make Albert Einstein visibly uncomfortable. He famously remarked, "God does not play dice with the universe." That line has echoed through nearly a century of late-night debates about physics and fate. But what does this randomness actually entail? In classical physics, reality works like clockwork. If you know the initial positions and velocities of all the particles, you can, in principle, predict the future with perfect accuracy. It's neat, deterministic, like lining up dominoes and knowing precisely how they will tumble. Quantum mechanics broke this mold. It replaced exact predictions with wave functions, mathematical clouds of probability describing all possible outcomes. When a measurement occurs, the wave function collapses into one outcome. But which one emerges isn't predetermined. It is genuinely random. This randomness isn't shorthand for ignorance. It isn't due to hidden mistakes or missing knowledge. It is built into the very foundation of reality. All we can ever do is compute probabilities and then accept whichever result manifests. Some interpretations try to soften this blow. The many worlds view, for example, proposes that every possible outcome does occur, but each in its own parallel branch of reality. Measure a particle's spin, and in one universe you see up, in another you see down. No randomness, just branching. But from your perspective, you still can't predict which branch you'll experience. The unpredictability remains. This provokes profound philosophical questions. If randomness truly lies at the heart of reality, What does that mean for cause and effect? For free will? For the very structure of physical law? It might seem unsettling, a universe not scripted from the beginning, but improvising along the way. Yet randomness is not the same as chaos. Quantum mechanics is astonishingly precise in its probabilistic predictions. It doesn't say anything goes. It says, here is the list of possible outcomes, and here are the odds. And when tested, like in the meticulous experiments of quantum electrodynamics, those odds have matched reality to 12 decimal places. That's equivalent to predicting the height of Mount Everest to within the thickness of a human hair. So yes, outcomes are random, but the tapestry woven from billions upon billions of these outcomes is stable, predictable, and ordered. That is why a coffee mug sits solidly on a table, even though the particles inside it are governed by uncertainty. In this sense, randomness is not a bug, it's a feature. It injects flexibility into the universe. It fosters novelty. It may even be essential to life, creativity, and consciousness. Consider evolution. Without random mutations, there would be no diversity of species, no flowering of forms. Randomness births leopards and leaves, philosophers and poets. Some find comfort in this unpredictability. A perfectly deterministic universe might feel like a prison of inevitability, where every thought and action is just the byproduct of mechanical laws. But a probabilistic universe offers space for surprise, for the unexpected. Of course, randomness also leaves questions unanswered. When a particle collapses into one state rather than another, why that one? Quantum mechanics doesn't provide a reason. It simply gives you the odds. It's like flipping a coin. The fact that it lands heads has no deeper why, only that it had a 50% chance. This carries weight. It suggests reality is not fully knowable in the classical sense. Certainty has limits. Beyond those limits lie ranges of possibility. And yet, even in this fog of uncertainty, we thrive. We build technologies powered by quantum randomness. We discover meaning in unpredictability. This tiny wiggle at the base of reality ensures that no two things are ever perfectly identical. Even identical particles can behave differently, carrying whispers of uniqueness into the universe. So yes, perhaps the universe does play dice, but it plays with such refined elegance that from those rolls emerge galaxies, atoms, minds, and time itself. And if quantum physics were only a collection of equations, strange, elegant, and precise, it would still be one of humanity's crowning achievements. But what elevates it further is its philosophical reach. It reshapes not only our answers, but our very questions. Reality, we thought, was solid and external, independent of us. But quantum physics gently challenges this. It suggests that, at its deepest levels, reality is not fixed, but conditional. Possibilities lie in wait, and observation nudges them into form. A particle in superposition is not indecisive. It's everything at once. A smudge of probability. Measurement forces it to settle, like the universe quietly choosing a story. This leaves us with a humbling thought. Perhaps we are not separate observers peering in from the outside. Perhaps we are entangled participants in the same unfolding dance. For scientists, this is a technical matter. For many others, it borders on the spiritual. Quantum physics doesn't hand out easy metaphors or shortcuts to enlightenment, but it does offer something valuable: humility. It reminds us that the world is stranger than our instincts allow, that the familiar solidity of daily life is just a filtered version of a much more peculiar reality. Schrödinger's cat is not really about cats. It's about living with uncertainty. It's about what it feels like to exist in states of possibility, until time or choice collapses them. And in that sense, it mirrors our own lives, waiting for a test result, hoping for good news, living in a haze of probabilities until clarity arrives. Quantum mechanics doesn't insist the world is unknowable. It simply whispers that it isn't obligated to be obvious. Maybe certainty is overrated. Maybe wonder lives in the gaps, in the forests of possibility where outcomes haven't yet solidified. As Richard Feynman once said, I think I can safely say that nobody understands quantum mechanics. And maybe that's the most honest statement of all. Quantum mechanics isn't something you conquer. It's something you accept, like a dream or a poem. Precise, predictive, and useful, and yet irreducibly strange. Perhaps that makes it more truthful, because the universe was never designed to make sense to us. It was only designed to be. So as we drift together through this quiet realm of quantum thought, the deepest lesson may not be about particles or probabilities, but about perspective. To embrace uncertainty as a feature, not a flaw. To loosen our grip on rigid knowing and rest instead in possibility. The quantum world reminds us that emptiness is never truly empty, that time can flex, that light can forget its script, and that even reality itself sometimes dreams. So thank you for coming along on this journey. Whether wide awake, peacefully drifting, or fully asleep, we've traveled together through slits, through cats in boxes, through rippling fields and mysterious experiments. We've met particles that masquerade as waves, and waves that reveal themselves as particles. And somewhere in the strangeness, we've glimpsed beauty. Perhaps that's the gift of quantum mechanics, not certainty, but wonder. A reminder that while the particles may be undecided, this moment, here and now, is enough. So, from the lazy scientist, good night.